In this video, you'll learn how truss elements are defined and their corresponding stiffness matrices are derived. A truss element is like an axial element, except that it can be orientated in any direction. Axial elements feature only a single degree of freedom per node, and they need to be orientated parallel to one of the global axes. So in this case, it's parallel to the x-axis, but it can also be parallel to the y-axis. A truss element can be orientated in any direction, and it has 2 degrees of freedom per node, a vertical component and a horizontal component. As such, this is a 2-dimensional element with 2 degrees of freedom per node. As there are multiple degrees of freedom per node, it is helpful to devise a labeling convention. Consider the following arbitrary structure comprising of truss elements meeting at a single point, this point being point I. At point I, we have degrees of freedom u2i minus 1 and u2i. To see how this works, let's just say that node I is in fact equal to 5, then our degrees of freedom are u2 times by 5 minus 1, which is equal to u9, and u2 times by 5, which is equal to u10. To define our element, we draw it in an inclined configuration. We have node I and node J. At node I, we have horizontal degree of freedom u2i minus 1 and vertical degree of freedom u2i. Similarly, at node J, we have u2j minus 1 and u2j. The axes that correspond to these degrees of freedom are the global axes, and these are x and y. There are also local element freedoms and local element axes, which we denote with an overbar. The local element degree of freedom for node I is given by u bar I, and the local element degree of freedom for node J is given by u bar J. These have a coordinate system called y bar and x bar. The element is in an inclined orientation, which we denote by the angle theta. Using the generalized formulation of strain energy discussed in the previous video, the strain energy for the truss element is given by lambda E equal to half times the transpose of the displacement vector in the local coordinate system times by the local element stiffness matrix times by our displacement vector, from which we subtract the transpose of the local displacement system times by our local element force vector. Again, we're using overbars to denote displacements and stiffnesses in the local member coordinate system x bar, y bar. The displacement vector for the truss element in the global coordinate system is given by UE transpose equal to U2I minus 1 U2I U2J minus 1 U2J. We need now to relate UE in the global system to U bar E in the local element coordinate system, and this is done through what's called the transformation matrix. To obtain the transformation matrix, we write down U bar I and U bar J in their component forms. In this case, U bar I is equal to U2I minus 1 times by cosine theta plus U2I sine theta. U bar J is equal to U2J minus 1 cosine theta plus U2J sine theta. To understand equation 3, we need to look more closely at our coordinate systems. Firstly, let's write down our global coordinate system given by x and y. We now pick a point P, which is given in polar coordinates, where the coordinates of this point are r and alpha, where r is the distance of point P from the origin, and alpha is its inclination. We now project point P onto the x and y axes to get values for U2I minus 1 and U2I. U2I minus 1 is our horizontal component, and U2I is our vertical component. Using trigonometry, we can see that U2I minus 1 is equal to r cosine alpha, and U2I is equal to r sine alpha. We now need to rotate the axes so that they coincide with the angle of the local element system, which in this case is inclined to an angle theta. We can draw this new set of axes on our diagram using red ink. The horizontal axis being x bar and the vertical axis being y bar. And as we said before, this is inclined at an angle of theta. We now project the point P onto the x bar axis, and this gives us our point U bar I. We can again see, using trigonometry, that U bar I is equal to r cosine alpha minus theta, which, using the double angle formula, we can expand to r cosine alpha cosine theta plus r sine alpha sine theta. From equations 4 and 5, we can see that cosine alpha is equal to u2i minus 1 divided by r, and that sine alpha is equal to u2i divided by r. If we substitute these values for cosine alpha and sine alpha into equation 6, we get the following expression. U bar I is equal to u2i minus 1 cosine theta plus u2i sine theta. We can now see that this is the same as the first line in equation 3. If we swap out the i's for j's, we can then obtain the second line in a similar way. So returning to equation 3, equation 3 can be rewritten in matrix vector form. So we have a column vector of u bar I and u bar j, and this is equal to a matrix of coefficients cosine theta, sine theta, 0 and 0, 0, 0, cosine theta, sine theta, times by a vector containing u2i minus 1, u2i, u2j minus 1, and u2j. We can then say that this vector here is u bar e, and this matrix here is T, and this is UE. Or writing this out again, we've got U bar E is equal to T times by UE. T in this expression is called the transformation matrix, and it allows us to move from one coordinate system to another. For the element stiffness matrix in global coordinates, we now need to use our transformed version of U bar E in equation 1. So all we need to do then is to substitute for U bar E in all of the terms in this equation. When we do this, we get the following expression: half times by UE transpose times by T transpose times by K bar E times by T times by UE, from which we subtract UE transpose T transpose F bar E. Just remember that the transpose of a matrix product causes that multiplication to reverse. So for example, U bar E transpose is equal to T times by UE, all transposed, which is then equal to UE transpose T transpose. We can then compare the terms in this and clearly see from what we've just said that U bar E transpose is given by this, and U bar E is given by this, and similarly we have the same here. The term T transpose K bar E T is actually now the element stiffness matrix in global coordinates. And similarly, this is the element force vector in global coordinates. From this, we're able to now make the following definitions. Firstly, the element stiffness in global coordinates is given by the transformation matrix transposed times by the local element stiffness times by the transformation matrix, and the element force vector in global coordinates is given by the transformation matrix transposed times by the local element force matrix. We now need to perform the matrix multiplication in equation 12. So firstly, we work out the transformation matrix transposed multiplied by K bar E. This gives T transposed K bar E, and that's equal to AE over L times by CS 0, 0, 0, 0, CS. Note that C is equal to cosine theta and S is equal to sine of theta. It's just a shorthand. They're multiplied by 1, minus 1, minus 1, and 1. This is a 4 by 2 matrix, and this is a 2 by 2 matrix. So this means that we'll end up with a 4 by 2 matrix. So we have AE over L times by CS minus C minus S minus C minus S, C and S. Then the final step is to multiply this one more time by the transformation matrix. So we have T transpose K bar E times by T. We've already done the first part of this multiplication. And now we're multiplying it again by the transformation matrix C, S, 0, 0, 0, 0, C and S. This now gives us a 4 by 4 matrix equal to AE over L times by all the components inside. So we have C squared CS minus C squared minus CS, CS s squared minus cs minus s squared minus c squared minus cs c squared cs minus cs minus s squared cs and s squared, and this is then equal to our element stiffness in global coordinates. For the element vector in global coordinates, we have A, E, alpha delta t times by minus c minus s, c and s. Finally, we can indicate the element degrees of freedom in the global coordinate system along the rows and columns of the matrices. So we have 2i minus 1, 2i, 2j minus 1 and 2j, 2i minus 1, 2i, 2j minus 1 and 2j, 2i minus 1, 2i, 2j minus 1 and 2j.